I'm happy to Jansen, and she's going to give an expository talk about the Borel-Serre compactification or Borel-Serre duality, as it says in her title. Thank you.
Okay.
Yeah, the screen will come back. The screen will come back in a second. Sorry, I moved something.
Good. Thank you. This is really weird. So thank you to the organizers for organizing and for inviting me to give this talk. So it will be an expository talk on Borel-Serre duality. So I feel that maybe we've seen, I'll be repeating some of what Peter said quite a bit, but only for the first half, and then we'll get kind of into the brief. And we'll see how I get on with this hybrid kind of thing. I thought it best to be on the safe side and do like a non-board talk. But I have to get used to actually people being there. So we'll see. But let's just get started. So just to set the scene, to make it as accessible as possible, we're just going to think about the special linear group. And in fact, we're going to be even more specific and look at finite index torsion-free subgroups. So this could be something like congruent subgroups. So given such a group, so whenever I write gamma for the rest of this talk, it will be a finite index torsion-free subgroup of SLNZ. Gamma is going to act freely and properly discontinuously on the following space. So we take the coset space given by considering SLN R over the real numbers and modding out by a maximal compact subgroup, special orthogonal group, and gamma acts on this by right multiplication. So this naturally has the structure of a smooth manifold. In fact, it's diffeomorphic to Euclidean space. So when we mod out by this action of gamma, we also get a smooth manifold. And moreover, this is a model for the classifying space of gamma. So now this allows us to study the discrete group gamma in terms of using geometric tools. We have this nice geometric classifying space. However, there's one hitch to all of this, namely that this is not a compact space. So for doing calculations and stuff, this is rather annoying because there's a lot of stuff that we can't do. So to remedy this, several compactifications of X mod gamma have been introduced, and the one we'll be looking at today is the Borel-Serre compactification. So let me give you, first of all, a very brief introduction to the Borel-Serre compactification. So it was introduced in 1973 by Borel and Serre, and we'll denote it like this, X bar mod gamma. So the three main properties of this space are the following. So first of all, it's compact. Secondly, it's no longer a smooth manifold, but it's not too bad either. It's a smooth manifold with corners. So by this, I mean it's modeled upon quadrants in Euclidean space. So we have this corner structure. And this inclusion identifies X mod gamma as the interior of this manifold with corners, which means in particular that this inclusion is a homotopy equivalence. So the Borel-Serre compactification is in fact also a model for the classifying space of gamma. So now we really do have a compact geometric model for the classifying space of gamma. So the cost of actually compactifying was this introduction of corner structure, but we haven't introduced any complicated singularities when we want to study this. We've just introduced this corner structure. The idea behind this construction is very roughly the following. So instead of compactifying X mod gamma directly, what Borel and Serre did was they constructed a partial compactification, or boardification, if you like, of X, and then extended the action of gamma to this partial compactification. And then the Borel-Serre compactification is just the quotient space when we mod out by this action. So this also is kind of reflected in this notation. So this is a very, very useful compactification. primarily because it is a model for the classifying space and it's not a very singular compactification. So just to name maybe two of the most, as far as I know at least, two of the most important applications of this, this space. First of all, we have some important calculations in algebraic K-theory due to Borel and to Quillen. So calculating the ranks of certain K-groups and also showing that these are finitely generated. And then secondly, we have this Borel-Serre duality, which is what we'll be talking about in this talk.
Mikala, are you saying that it's not compact before?
It's not compact before. No. So partial compactification is not kind of, it's not a well-defined thing. It's just kind of reflecting the idea of what you do, but it's not compact. X bar is not compact, but the action is co-compact. Okay, so I'm going to talk about Borel-Serre duality, and what we'll do is, first of all, I want to state the theorem of Borel-Serre duality. This will be a slight recap of what Peter said in the introduction. So I'll introduce kind of the necessary notions to make the right statement, and then I want to give you a kind of an outline of the proof, which, like, the outline of it is not so complicated. It's quite easy to follow. But the main technical ingredient is this partial compactification X bar. So I also suspect that this is perhaps the main black box that people have with regard to this result, actually kind of using this partial compactification. And the proof really doesn't just use that we have any partial compactification like this, it really uses the explicit structure of it. So I want to get back, once we've given the outline of the proof, I want to get back to this construction and give you an idea of how we construct the Borel-Serre partial compactification. So you have an idea specifically of how this dualizing module comes into play, which is the Steinberg module, as we saw before. So I want to see how we kind of get the Steinberg module out of this compactification. So we'll get back to this afterwards. Okay. So first of all, this notion of duality groups. So this is due to Bjerre-Ekman. I think there's a slide. If it's too annoying when there's this lag, then let me know, because things are going a little bit faster on my screen. This was done around the same time as Borel-Serre did there. Next up, I think the papers are from 73, both of them. So G is a duality group of dimension n with respect to a right G module D. If we have a class in this homology group, so the degree n homology with coefficients in this D, such that cap product with E induces an isomorphism between the kth cohomology with coefficients in some module A and the n minus kth homology with coefficients in this twisted, if you like, coefficient module. So we have to tensor by this dualizing module D. And this should hold for all coefficients A and all integers K. So you can think of this as some kind of Poincaré duality with a twisting of the coefficients. So if this dualizing module, which we call it, so let me write that, we call D the dualizing module G. If this dualizing module is just with integers with a trivial action, then it's just, this is just Poincaré duality. So this is kind of generalizing, saying that we have this duality thing, but when we get this pairing between cohomology and homology groups, we need to twist the coefficients by some module. So as you see that this definition, this dualizing module is not specifically given, but it's quite easy to show that if there is this duality, then it has to be this homology group, this cohomology group with coefficients in the group ring, as Peter showed. So this is quite a simple exercise, but it doesn't necessarily tell us much about the dualizing module, because we still need to kind of determine the cohomology group and the action.
Sorry, so you insist that D is a right G module and A is a left one, but I guess you also don't take the next module as well over G, right?
No, so this is over. and then with the diagonal action. Okay, so now I'm going to introduce the, so to state the theorem of Borel-Serre duality, so specifically for these torsion-free finite index subgroup of the special linear group, we need to introduce the Steinberg module. So here I'm just repeating what Peter said. So we let Sn denote the poset of proper non-zero subspaces in Q to the n. And then the Tiff building is the simplicial complex we get when we take the realization of the nerve of this poset. So more specifically, when we look at this simplicial complex, a P cell in the Tiff building exactly corresponds to a flag. So a sequence of proper inclusions like this. In Q to the n. And the homotopy type of this simplicial complex is determined by the Solomon-Tiff theorem. So we know that this is homotopy equivalent to a wedge of n minus 2-dimensional spheres, and it's a countably infinite wedge, in fact. But we won't need that for this talk. So all we need is that this means that its reduced homology is concentrated in 1 degree, in degree n minus 2. So given this theorem, we can define the Steinberg module as this non-zero reduced homology group. Like this. So maybe I should specify that this is integer coefficients. And the action of SLNZ on this is simply given by the action of SLNZ on Q to the n, and then the induced action on this poset of subspaces, which in fact we're just acting on, when we're given a cell which corresponds to a flag, we just act on each subspace in these flags. Okay, so this is all I'm going to say about the Steinberg module, but I think there'll be more talks kind of specifying what, kind of looking at the Steinberg module more specifically. So with this, we can state the theorem of Borel-Serre duality. So gamma is a duality group. So gamma was this finite index torsion-free subgroup of dimension n choose 2 with respect to the Steinberg module. So let's spell out exactly what that meant. So we have isomorphisms from between cohomology groups with coefficients in some module A, and these homology groups shifted by this n choose 2 with coefficients in this twisted coefficient module. And this holds for all A and all K. Note that we don't actually specify, in the definition of the duality groups, we don't actually specify any naturality, but this isomorphism is given by a cap product. In fact, one can show that if we have isomorphisms, then it has to be given by a cap product. And because it's given by a cap product, we're going to get this naturality for free. We're also going to get a kind of a nice compatibility between long exact sequences in cohomology and homology. So this is all because it's all, these isomorphisms are explicitly given by the cap product. So before moving on to the proof, let's just give two very simple corollaries really relating this to high dimensional cohomology. So first of all, this determines the cohomological dimension of gamma, which is the same as the virtual cohomological dimension of SLNZ. So this is n choose 2. And we can kind of look at this top cohomology group and spell out this isomorphism. Then this is just the co-invariance of this Steinberg module, like so. But this is also why, I mean, this is a nice expression for this, but this also means that we need to understand what the Steinberg module actually looks like as a gamma module.
And you stated for a finite index subgroup, but it is also true that for the module,
I will have a small remark on that at the end, but it's so.
Can you repeat the question?
Yeah, sorry. So Natalie asked if, so I state this for a finite index subgroup, but is this true for all of SLNZ?
This doesn't really sense.
It is true, but the point is that here I'm taking A is any gamma module, whereas for if we don't have this torsion-free thing, we need to be careful about the torsion in these modules. But here we don't. We kind of get to just ignore. We can take all modules. So this is why for SLNZ we work over the rationals. It's just to have a nice classifying space. Sorry, I don't know if I understood the question. The torsion doesn't really, should I say the torsion is just, or the torsion-free condition is just to actually get a nice classifying space so that everything kind of runs through smoothly. But these coefficients, I'm going to use the theorem, which implies duality, but where we don't look at arbitrary coefficients.
Yeah. Was the virtual dimension of SLC known first, or was this computation of it?
I believe this is the computation of it. Yeah. And as I said, this is really Borel-Serre did this kind of simultaneously with Bierry-Ekman's development of duality groups. Okay, so to prove this, we're going to use the following theorem. So this perhaps also answers Natalie's question from the previous talk about kind of identifying the dualizing module. So if we have a group of type FP, so recall that this is, we have a finite G projective resolution of the trivial module. Then if we have some integer n such that this cohomology, so cohomology of G with coefficients in this group ring, this is free abelian in exactly this degree, and it's trivial otherwise, then G is a duality group of dimension n with respect to this non-trivial cohomology group. So first of all, as I said, it's quite easy to show that this has to be the dualizing module. But then in using this theorem, actually identifying this dualizing module is kind of part of proving it. Like we can identify this and show that it's free abelian. This is also, you see that this is quite, in some respects, it seems like a simple way to prove duality because we don't really we have nothing about these arbitrary coefficients. All we need to do is identify this cohomology. Okay, so to apply this, first of all, let's note that gamma is of type FP. In fact, it's of type FL, so there's a finite G free resolution of this. So this is simply a consequence of the fact that this Borel-Serre compactification is a model for the classifying space of gamma, and it's a smooth manifold. It's smooth manifold with corners. Topologically, it's a manifold with boundary. So it has a nice, we can equip it with a finite triangulation. So it has a structure of a finite CW complex. And this means that if we have a triangulation of X bar mod gamma, we can lift it to a gamma invariant triangulation of X bar, which is the co-simplicial complex of this, is exactly going to give us this finite free resolution. So I want to stress here that to get this, we only use existence of a compactification of a classifying space which has the structure of a finite CW complex. So we're still not using explicitly the structure of the Borel-Serre compactification. So this is not where the technical stuff comes into it. Okay, so we can use this theorem. We have a group of type FP. So let's analyze this cohomology. So the dimension of X bar is this. You can try to calculate this, or you can just trust me. So First of all, this was what I think Kaiuva also gave this geometric interpretation at the end of the previous lecture. So this cohomology group can be interpreted geometrically as the compactly supported cohomology of X bar. So this is also
X bar. Oh no, X bar is not.
X bar is not compact. No. So this also just uses that we have this classifying space which has the structure of a finite CW complex. This allows us to use Poincare-Lefschetz duality and convert this to homology, where we shift by the dimension D, and we get this homology of the pair, so X bar on the boundary. And then finally, the long exact sequence of this pair gives us an isomorphism here with the reduced homology of the boundary, shifted by 1 degree. So this just uses the fact that we have this inclusion of X into X bar, which is the homotopy equivalence, and we know that this is contractible. So X bar is a contractible space. So this is quite a general kind of identification. This doesn't help us much because we still need to know what the boundary looks like. And this is where the main technical stuff comes in, namely actually the explicit structure of the Borel-Serre compactification or partial compactification. So the homotopy type of the boundary is exactly that of the Tiff building. So given this, this is just the reduced homology of the Tiff building. So we know by the Solomon-Tiff theorem that this has the motif type of a wedge of n-2 spheres. So this means that this cohomology group that we were interested in to begin with is concentrated in degree n-2, where it is in fact free abelian. So this happens if and only if I is n choose 2, and it's trivial otherwise. And this is exactly what we needed to apply this theorem of Pierre-Ekman. So I've written it out again here. So we have a group of type FP, that is true. We have an integer, n choose 2, such that this cohomology is free abelian in this degree, and it's trivial otherwise. So we conclude that gamma is indeed a duality group of dimension n choose 2 with respect to this dualizing module, which we furthermore identified as the reduced homology in degree n-2 of the Tiff building, which is how we define the Steinberg module. Of course, one should be a little bit careful about the module structure, but this homotopy equivalence between the boundary and the Tiff building is compatible with this gamma action. So, assuming this homotopy equivalence, we are done. This is the proof. This is all that's going on. But I do want to spend a little bit of time on this and tell you what the Borel-Serre partial compactification looks like. So this is a very technical construction. So I'm trying to kind of, hopefully, I'll make it as accessible as I possibly can and still convey to you kind of the idea of what Borel and Serre did. So we need to talk about parabolic subgroups in SLN, but we can focus on these standard parabolic subgroups, namely things that look like this, these block upper triangular subgroups. I call it P or Q or something like this. So this is a subgroup in SLN, which I can picture as just a one block subgroup. So these are matrices of this shape. So we have these diagonal blocks, which can vary in size, and we have zeros below these diagonal blocks, and we can have stuff going on above the diagonal blocks. I also need to take all the SLNZ conjugates of these. But for kind of illustrative purposes, it's really enough to look at these block upper triangular subgroups. So I'm kind of going to ignore this SLNZ action because it'll come in kind of in various places, but you can really just focus on these block upper triangular subgroups. Okay, now the main idea of this construction is that of a geodesic action. So we define this geodesic action as follows. Given a parabolic subgroup P, something blocked upper triangular like this, we consider the subgroup AP of diagonal matrices such that each diagonal block is a positive scalar. So these diagonal blocks kind of correspond to the parabolic subgroup P. So if this is P, then AP looks like this. So I'm going to draw the outline of P like this. And then we have a positive scalar matrix here, another one here, and another one here. So in each block, we just have a positive real number specifying that scalar matrix. So note that AP is just a group like this. It's a copy of a product of copies of the positive real numbers of dimension KP, where this KP is the rank of P, and this is just equal to the number of blocks minus 1. So note that in this case, we have a positive real number here, we have a positive real number here in the middle, and then by the determinant condition, this one is completely specified. So instead of you can think of it as these diagonal matrices, this is the way we define the action, but this is also a very important part of this thing, that it's really just kind of an open quadrant in Euclidean space. So now we define this action. So we've defined X as this coset space, SLNR modulo this maximal compact subgroup, the special orthogonal group. It turns out that we get the same thing if we replace SLNR by P. So I can do this and look at this coset space, P modulo a maximal compact subgroup in P, which is just P intersect the special orthogonal group. So this is really just the orbit stabilizer theorem. So we have P acting on this X by right multiplication. It's going to be transitive, and we get this nice identification of X as this coset space. With this interpretation of X, it's quite easy to define an action of AP on X. We simply act by left multiplication.
So like P here, you mean sometimes of SLN and sometimes of SLR.
No, I always mean of SLR.
Oh, okay.
So I could write P of R, but I mean
Okay, thanks. Sorry.
real things in there.
What do you mean by each diagonal block is supposed to be scalar?
So I mean that the blocks are specified by P. Yeah.
You have a bunch of blocks.
So I have a bunch of blocks, and this block should be so you pick some positive real number and multiply it by the identity. Yeah. So the point is that we have diagonal matrices, but within each block, the entries have to be the same. So we act by left multiplication on this representative here. So this is well defined because AP is going to commute with this subgroup. So you can check this if you like. So we can't define it directly on this representation. We really need to identify X as this, this coset space, and then define it by left multiplication. So now we have this right action by gamma acting from the right, by right multiplication on this, or on this if you like, more or less, that's not the right, on this. And then we have this left multiplication acting on this, using the fact that we can meet with the subgroup that we are taking coset space with. So there's a nice kind of interaction between these two actions. They don't commute, which is quite a kind of crucial thing with this construction. Moreover, what we really want to do is, we've defined this for a fixed parabolic subgroup P. What we want to do is we want to define geodesic actions for all parabolics P. We define it in exactly the same way, but because they really depend on this identification, it's not completely obvious to see how all of these different actions interact. And that's like somehow really the technical stuff going on, that we need to identify these actions in a way that we can compare them. I won't get into that, but there's a nice compatibility between these geodesic actions according to inclusions of parabolic subgroups. So if we have inclusions of parabolic subgroups, then these actions are in some sense compatible.
Why are they called geodesic actions?
So they're called geodesic actions. So there's an exercise for this where you can look at what's going on in the SL2 case, and you can identify these orbits. And maybe there you can see why it's called geodesic. You really see the geodesic showing up. The point is that it's the orbits of AP are totally closed geodesic manifolds. So I've just talked about the smooth manifold structure, but there's also a lot more going on. So the orbits really kind of, they really come out nicely with these geodesic submanifolds.
Aren't they even flat?
I couldn't hear that.
Aren't they Euclidean flats inside the symmetric space?
If the orbits are Euclidean flats inside the symmetric space?
Yeah, is that true?
It depends what you, I don't know. Probably. We'll look at the orbits in a second. You can see, I don't know what exactly you mean by Euclidean flat, but it's true that there's a nice decomposition into the orbits, but that's exactly what I'll be moving on to now. Maybe what I say next will answer your question. Okay, so what we do want to do is we want to look at these orbits. So we're going to use these orbits to define Borel-Serre corners. So first of all, we set EP is going to be this quotient space will be modeled out by this action. And I will tell you that this is Euclidean space. Like so, we just have this is D is the dimension of X, and KP was this rank of P, so this number of blocks minus 1. Then it turns out this action, this geodesic action, turns X into a trivial AP bundle. So we have this trivialization of X like this, so completely decomposing it into the orbits of this action, into these AP orbits. And what we want to do is we want to partially compactify these orbits. So what do I mean by partially compactify the orbits? Remember that AP is this product of positive real numbers. By partially compactifying, I just want to add 0 to each of these factors. So we're going to define AP bar simply as a product of non-negative real numbers of the same dimension, and we have this canonical inclusion of AP. So what I want to do is I want to replace AP in this trivialization. I want to replace AP by AP bar. Rather, I want to add the stuff that I've added to AP. I want to add this to X. So to do this, we do this as follows. So we define the corner associated to P, denoted XP like this, as follows. So we take AP bar, product X. We have a diagonal action on this by AP. So we have AP acting on the left on X, and we have it acting on the right, from the right on AP bar, simply along this inclusion. So when we mod out by this action, we just get this Borel construction. And it turns out that this trivialization of X extends or induces a trivialization of this Borel construction. So here we just get the product of AP bar and EP. So this is what we wanted to do. We wanted to partially compactify each orbit. So this is kind of in terms of what it looks like. It's this quadrant of dimension kp and this product with a Euclidean factor d minus kp. So you can picture it like this. We have this quadrant in Euclidean space and some Euclidean factor. So this is this corner structure. This one?
Yes, over here.
The other way, there's an action of AP. So how is this defined? So how is this defined? So it's just we have an action, we have this product of AP bar and X, and we have a diagonal action on this by AP. So it's just acts from the left, it's just acting on the left, from the left on X and from the right on AP bar. And this is just via this inclusion, this action on AP bar. And then we just mod out by this. And this is somehow just identified, it's just a way of gluing. So to each AP orbit up here, we just glue AP bar to it along this inclusion. This is really just what's going on. So we just have this AP orbit, and then according to this identification, which there's a canonical such identification, it's not just a random thing. According to this identification, we just add these zeros to each coordinate. So we add this or this boundary to this quadrant. Okay, so this is partially compactifying the orbits of the geodesic action given by P. But what I want to do is I want to partially compactify the orbits of all the geodesic actions according to all the different parabolic subgroups at the same time. So this is also some technical stuff, but I just tell you that if we have P a subgroup of Q, these are two parabolic subgroups, then in fact we get compatible embeddings so that the corner associated, to Q embeds into the corner associated to P. So note that we're reversing conclusions. And these corners, these embeddings respect this corner structure. So that these kind of identifications of these corners as a quadrant and Euclidean factor, these are compatible with these embeddings of corners. So this means that I can now glue all of these corners together along all of these embeddings, and in that way, partially compactify everything at once. And this is exactly what I want to do. So I define X bar to be the union of all of these corners. So this, for one, it gives me a topological space. I'm really gluing things together. I'm just taking the topology of each corner. But at the same time, I'm also defining a manifold with corners, because each of these pieces is just a chart in a manifold with corners at S. So of course, there's some work involved in showing that we have these nice compatible embeddings and that this is all very nicely compatible with the gamma action and so on, and compatible with this corner structure. But this is essentially just what's going on. So just to summarize, what Borel-Serre did was they defined these geodesic actions and identified the kind of the non-co-compactness of the action of gamma on X to be what's going on when I move out along these geodesic orbits. And then what they did was let's just compactify these geodesic orbits. And we just compactify all of these at once. Okay, so as I said, there's kind of quite a small technical but not so difficult exercise on the SL2 case, which is nice, at least for seeing that things are geodesic. Also because it's in the SL2 case, this X is two-dimensional, so it's something that we can actually picture. But it has the problem of being almost a little bit too easy to actually see what's going on in this Borel-Serre compactification, because we don't actually see any explicit corner structure. So instead, I want to show you what happens in the SL3 case, at least kind of the intuition of it. So in this case, X is five-dimensional, so we can't really get the whole picture. But for the corner structure, we're still it's still okay, because these last three dimensions actually turn out to not have anything to do with the corners. So first of all, we have the parabolic subgroups. So if we just look at these block triangular things, then we have these three. So the problem, I could say, in the SL2 case is that we only have one parabolic subgroup. So there's no gluing going on. We just have this one geodesic action. So here I'm going to call these B, P, and Q. So let's see what the corners look like. So first of all, XB. This is a product like this, AB bar and EB. So this is a copy of products of non-negative real numbers. So the number of these, the number of copies is the rank of B. So it's the number of blocks minus one. So in this case, we have two. Yes, I should take one in each context class. But then the problem here is that I'm taking a finite index torsion-free subgroup. So I don't, I should be taking a few more, yeah. And then we have this three-dimensional Euclidean space factor, which is this EB. For P, we have this this product, and here we only have one copy of the non-negative real numbers, because we just have two blocks. So we have two blocks minus one, and here we'll get this four-dimensional Euclidean factor. And for Q, it's the same thing, because we only have two blocks. So these two corners look the same according to this. So the difference is going to show up in the way that they embed into XB. So here we'll see how they differ, these two. So let's have a look at that. So we have XB, XB, and XQ. So XB is something like this. We have this two-dimensional corner, two-dimensional quadrant, and then we have this Euclidean factor. So I'm pulling out this three-dimensional Euclidean factor of all of these, so we can see what goes on in just the two first. Then for XP, we have this factor, and then one of these Euclidean factors. So we get something like this. So these embeddings are just kind of the way they're pictured. And in the Q, we get the same thing, but it's just in the other direction. So here we can identify, so the interior of this is exactly an AB orbit. So our partial the inclusion is from the bigger parabolic to the smaller parabolic.
But the space is how big.
The spaces include, so here we have, so I'm shrinking, so that's a nice thing. I'm shrinking this R to just be the positive.
About the line that
Forget about the line. Let me give you these orbits, and maybe you still have the question afterwards, and then ask me again. But let me see if it helps when I do. So this is an AB orbit, all of this interior. So what I'm doing when I'm compactifying, partially compactifying, is I'm adding all of this boundary to this quadrant. So I'm adding all these zero coordinates, like both zeros in both factors. Over here, an AP orbit is a line like this. So maybe answering Peter's question, this real line coming from over here sits as kind of transversally here and identifies with this part here. So you should kind of, here I have all the real numbers, and here I only have the positive real numbers. So I'm kind of, there's a little bit going on in that identification. So partially compactifying this orbit is adding this 0 up here. And then of course I do that for all the orbits. So I get this whole boundary up here.
Right. Like
Not here.
X, Y, X, Y, or
So the real numbers, as rather the positive real numbers, may have been an easier way to see the inclusion. I think that's what you're doing here. You don't have all the real numbers; you have the positive real numbers, which is of course homeomorphic to the real numbers.
Yeah, so I could do this just to
That
be.
might be helpful for understanding.
Is this nice? There we go. Yeah.
That makes sense.
So the point, like in comparing these coordinates, the difficulty is exactly in that this action is defined on the coset space where the coset space is taken with respect to the parabolic subgroup, and I don't necessarily have like kind of a complete translation between them. So then in Q we do the opposite, so it goes this way, the AQ orbit. So partially compactifying this, I'm adding this 0 over here. And then, of course, I should be taking the SL3Z conjugation into account, and I'll be gluing all of these pieces together along conjugations and the way they interact, and they are included in each other. Okay, so this is a nice way to define this space as kind of gluing all these things together, because we get topology, we get the structure of the manifold with corners from the very beginning. But for analyzing this, and especially for identifying the boundary, maybe this is not so useful. So what we want to do is we want to identify a nice partition of the partial Borel-Serre compactification. So to do this, we're going to identify EP as a subspace of X bar, and I'm going to call this a boundary component associated to P. So we do this as follows. So we take EP, and we can kind of canonically include it into this product by including it at the origin. So all these coordinates are 0. We just include it at that point. This is a way to identify the corner associated to P. And this, by definition, is just a subspace of X bar. So this is somehow just identifying the corner point of what we've been adding. So note that it's not, we're adding more boundary to the orbit, but in identifying the boundary component, we keep picking out the origin. So we're only picking out this one point, but then maybe we may have added more boundary to the orbit in our partial compactification. So with this identification, it turns out that we can write X bar as a disjoint union over P of these EPs. So a disjoint union, not topologically, but as a partition. And here we have EG is equal to X. So G is SLM. So the boundary component associated to the whole group is the interior. So this is a nice partition of it, but to understand kind of topologically what's going on, we can look at a specific boundary component, EQ. We can take its closure and see what do we get topologically when we take the closure of this boundary component. There's a nice, exactly kind of analogous description of this, or partition. So it decomposes.
You mean the boundary? It's
No.
we don't.
because I include the interior as the boundary component associated to the whole group. I'll be getting rid of it in a second. Yeah. I'll be returning to the other thing in a second. So here we get a nice partition, but where we only take parabolic subgroups that are subgroups of Q. So this kind of exactly generalizes what happens here, since we can just identify X as the boundary component associated to EG. So topologically, these boundary components kind of what the things that are glued onto to the boundary component associated to Q exactly correspond to the parabolic subgroups contained in Q. So a way to interpret this is by saying that X encodes the posets of parabolic subgroups. So we have a boundary component for every parabolic subgroup, and the closure relations are exactly given by inclusions of parabolic subgroups, and there's nothing else going on. And moreover, each of these boundary components, because it's just a Euclidean space, it's just contractible. So there's really nothing else going on. It just encodes the poset of parabolic subgroups. So when I take the boundary, I just get rid of X. So I'll just be taking this partition over proper parabolic subgroups. So the boundary encodes the poset of proper parabolic subgroups. So this partition is what we need to kind of get at the TIPS building and the Steinberg module. So let's return to this SL3 example and see if we can identify these boundary components in this case. So EB, first of all, I identify this as a subspace of the partial compactification by including it at the origin in this AB bar. So this is just identifying EB as this corner point across this factor. EP is identifying it by including it at this origin. So here I get all of this. This is EP. So by embedding it, this is identified over here. And EQ is this part here. So what we get is kind of this is the boundary of X bar. And then these little pieces should be glued together along the SL3Z action. So we're going to get some kind of infinite polygon. They're all going to glue together in some way. So note in particular that this is some kind of slight, I think, a little bit of cause of confusion in that the boundary component associated to B is a lot smaller than the boundary of the corner associated to B. So this is kind of a thing to be aware of. The smaller the parabolic subgroup, the more boundary we're adding in our partial compactification of the orbits, but the smaller the boundary component, because it's really just picking out the origin. Okay, so I hope this gives you some idea of what's going on. So let's see how the TIPS building shows up. So if you've seen parabolic subgroups before, you can guess what's going on. So parabolic subgroups correspond to flags, and this is how this translation is going to work. So let's make this slightly more specific. So this is the identification that Borel-Serre did. Oh, see if I can get through. So let P be the set of maximal parabolic subgroups, and we have this cover of the boundary. So by maximal parabolic subgroups, I do not include SLM. I mean maximal proper parabolic subgroups. So we take the boundary component associated to such a maximal one, and we take the closure of it. So because of this decomposition, that the closure of this has a partition into boundary components associated to all parabolic subgroups included in Q. because we're taking all maximal parabolic subgroups, this accounts for all parabolic subgroups, so we get the whole boundary. This is a locally finite cover of the boundary, and the nerve of this cover is, first of all, homotopy equivalent to the boundary, to what it's covering. So this is, there's also some technical work included in this, but this is a kind of a case of the nerve theorem, identifying when the nerve of a cover is homotopy equivalent to what we're covering. I won't get into this. And it is the TIPS building. Now I'm just saying it is the TIPS building, kind of depends how you define the TIPS building, but this is what Borel-Serre writes, because they do it kind of in the opposite order. So let's see why it is the TIPS building. So we're just going to look at the P cells in these two subtissue complexes, the realization of the nerve of this cover, and the TIPS building. So a P cell in here corresponds to a choice of maximal parabolic subgroups that satisfy that the intersection of the associated pieces of the cover, these EQIs, the closures of these boundary components, is non-empty. That's the definition of the nerve. In the TIPS building, we have a flag. Now, the correspondence is then simply a case of identifying the fact that this is non-empty if and only if the intersection of the corresponding group, so ignoring that we have this, this cover condition, that this intersection is a parabolic subgroup. So if it is a parabolic subgroup, so let's call it, I can't write that way, let's call it P, then this is just this boundary component associated to P. Then this translation here is just, yes, thanks. Then this is simply a case of showing that flag, or using that flag, so in bijection with parabolic subgroups. So a parabolic subgroup is a stabilizer of a uniquely given flag. So this is why the TIPS building shows up. This is why the Steinberg model shows up. Then you need to think about the action of gamma on the parabolic subgroups and these flags, but this all works out nicely. Okay, so I hope this gives you, this is what I have on the Borel-Serre compactification. So I just want to kind of recap the theorem of Borel-Serre duality, because that's kind of the important thing to take away, at least in terms of the tool, and not kind of this ingredient in the proof. Oh, no, I've got a slide. Wait, let me do this as well, because it's fun. Do I have enough time? Is that okay? 3 minutes? I'll do this quickly. So just to note that this, how this identification works, we have dx bar is glued together out of these pieces, so these corners, and then via some SL3Z action. And the TIPS building is glued together out of something like this. So we have this subspace generated by the first standard basis vector. We have this one generated by the first two. And then we have the corresponding flag, because there's inclusion between these. And then here we simply get this correspondence. So P is the stabilizer of this subspace, Q is the stabilizer of this subspace, and B is the stabilizer of this flag. So you also see that it's really a homotopy equivalent, because we get some dimensions switching around in this stuff. Okay, so let's recap Borel-Serre duality, and then I have just a few short remarks on kind of the more general picture. So any finite index torsion-free subgroup in SLNZ is a duality group of dimension n choose 2 with respect to the Steinberg module. So by definition, this is simply saying that we have a class E such that the cat product by E gives us an isomorphism between these cohomology groups and then these homology groups where we have a degree shift and we have this twisting of the coefficients. So here, as I said, because we work in torsion free, we can work with any gamma module. This holds for any gamma module. So in the general case, this is done in this, there's some, we get, this holds more generally, but then we need to be careful about the torsion. So we have, for example, these are three things that kind of work more generally. So we have these virtual duality groups, for example, SLN said. So here we just need to be careful about, as I said, torsion in the group versus torsion in the coefficient modules. So generally, if the torsion is in the group, then it shouldn't be allowed in the coefficient module. So all of this holds for SLN over the rationals. Borel-Serre, they do this for general S-arithmetic groups. So for example, we also get these symplectic groups and the general linear groups. So here you need to be careful about that there might be some orientation module showing up if the action of GLN-Z is orientation reversing, that we need to take this into account. We could ignore this for SLN-Z. And then finally, just for completeness, they work, Borel-Serre work over number fields in full generality and not just over Q. And this is all I have to say.
Questions? The previous slide. So yeah, this is what I was trying to remark, that if you remove the torsion, I mean, then like you are applying duality, which holds for coherent modules, coherent sheet over PG. But when you remove the torsion, like all representations need not be coherent, will be possible. In order to put the coherentness,
so in order, so this is more of a comment. I'm not sure I'm the right person to kind of translate this comment. So it's Borel-Serre duality. If you don't have this torsion-free condition.
If you don't have this torsion-free condition, every A module is going to be a quasi-coherent sheet.
Every A module is going to be a quasi-coherent sheet over BG.
But in order to apply duality, you need coherent modules, and that's why you need the torsion-free in the coefficient.
Okay, so in order to get Borel-Serre duality, you need coherent modules. So that's why you need this torsion-free condition. Yeah. So it's really just, you just need to be careful. This was just allowing me. This was just taking torsion-free was just allowing me to not be careful about anything, because we really have a classifying space, and we get this duality for all modules.
Another question, Andrea?
When you say over number of fields, I'm just curious, you mean also the integers? So you replace Z, SLN?
Yes, so then we replace Z by the ring of integers in a number field.
Then, can you repeat what the definition of parabolic group is? In the sense of, you make examples with the block matrices, and then you say something like, then you have also to consider the conjugate subgroups, but now conjugate is with respect to SLN-Z.
No, so this is, I can do this in, sorry, so what should I replace parabolic subgroups by in the general case of number fields?
No, I still, sorry, consider just Z. Yep. And the parabolic subgroup arises as a subgroup of SLN-R, right?
So, I mean, I think.
But you have to conjugate by, I mean, at the end you don't want more than half of many.
No, so you need, so a lot of this is really uses that we want the field to be countable. Maybe it should be a countable number. Is that part of it?
Yeah.
Yeah. They work. So they work generally over fields. Maybe they work generally over fields, but then you have to look at algebraic groups and parabolic subgroups of algebraic groups. So you need to be careful about. I always get a bit scared about parabolic subgroups, because you have to be careful about if it should be a subgroup of the algebraic group. It should be an algebraic subgroup that is a subgroup of the algebraic group. In this case, everything works out fine, but there is kind of something to be aware of if you have algebraically closed fields or not. In this case, it's also, it's okay to take these standard ones and then conjugate them just by SLNZ. Generally, I should be taking conjugates over SLNQ. Here it turns out to be the same. So I'm not sure that if for general number fields in what generality that should hold. In this case, I can really just focus on the standard ones and then take SLNZ conjugates, which is kind of helpful for intuition, I think. Generally, parabolic subgroups, you just take parabolic subgroups and they include all of these conjugates.
There was another question. Yeah. So, wait, you mentioned at the sort of start that the Tiff building was sort of isomorphic to diffeomorphic, homeomorphic, sorry, to number of circles or number of spheres.
Homotopy equivalent.
Homotopy equivalent. Okay.
Yep.
So does this XP sort of correspond to one of these, or really can't really say that?
No, I don't think so.
Yeah, part of it too.
Yeah, so you need this apartment, as Peter was talking about, these apartment that generate, which were given by these bases. So I think this is kind of saying, this is why this Borel-Serre compactification is motivating why the TIPS building shows up. But I don't know if it's necessarily the right way to understand the Steinberg module better. So you still need, now we've identified the dualizing module, but you still need to understand the Steinberg module.
Yeah, probably another question. So I will just talk about this Steinberg module. Is it sort of, and to say that it's the Steinberg representation of GeoM?
Yes. Yes. Is this, so the question was, is the Steinberg module the same as the Steinberg representation of GeoM? Yes. Yeah.
You can really write it as well.
Yeah. Yeah.
All right, more questions, maybe online question? No? We're here. If there are no more questions, let's thank Mikala again. Before you leave, I have some announcements.